I'm good. How are you? Hey? I thought I
Okay.
Yep. Okay, we're going to try and keep on time, or as close as possible, because that's supposedly what we're famous for. I'll give you 30 seconds to sit down. 15 seconds. Okay. Stefan, who's a virus researcher for Bitdefender,
Thank you.
is going to give us a presentation about something that I find truly fascinating.
Okay, so my name is Stefan, and I'm going to talk about ways we can use the end-user license agreement in order to classify binary files as being either clean or potentially unwanted applications. So we're going to talk about malware evolution for the nostalgics, and where potentially unwanted applications enter the scene, and of course about the end-user license agreement. That is the main topic. And how it integrates in our experiment and the processing flow we used in order to obtain our results. And of course, at the end, we have the conclusions and the questions and answers. So, the malware evolution. In the past, malware provided a statement about the creator's abilities, and actually, it wasn't that uncommon to find some sort of a signature in the binary files, a name identifying an individual or a hacker group or something like that. And that actually had a pretty good reason, because writing malware, it's time-consuming and needs a lot of information, a lot of working. So the next step, if you're already going to work for that and invest a lot of time, is of course monetary gain. And you can see a trend in the last few years where malware tends to go towards this monetary gain. It tries to earn as much money as possible. And actually, we had at VB14 here some really interesting presentations about botnets and networks like that. And actually, you can find that monetary gain is one of their back-end reasons. But working in such an environment is actually dangerous and might have serious legal implications. So why not enter the advertising market? Because the IT market itself is huge. So this is where potentially unwanted applications enter the scene. Now we have a broad definition. We define potentially unwanted applications as computer programs that in some circumstances employ techniques that circumvent security measures or have a negative effect on the user's interaction with specific applications or actions. Okay, so this is rather broad because it includes adware, it includes bundlers, and other kinds of applications. Now, some companies actually call this kind of software potentially unwanted programs, or PUAs. So this kind of software actually walks on a dangerous path somewhere on the limits of legality. So is it worth the risk? And we think it does, because having a large user base actually increases the earning for these software companies. And this is sometimes achieved with the help of social engineering, and this is mostly the case for bundlers, and even clandestine installations. And yeah, this is mostly for adware or more aggressive adware. And we have here in the picture, this is a evolution for potential unwanted applications, and the data are presented by our company. So it presents the evolution of potential unwanted applications from April 2014 to May 2014. And you can see that trend is quite obvious. And actually, in the last few months, we have a large spike in encountering such applications. And this is partly due to the fact that there are, I don't know, having a larger campaign, and more and more companies emerge. And also, the AV companies are trying to become more, I don't know, let's say, have more generic detections and things like that. So how do this kind of companies actually maintain themselves on the clean border? Yeah. Some of them, and most of them actually, benefit from the fact that they present an end-user license agreement to the user. So what are the implications of the user accepting such a document? Well, in some countries, the end-user license agreement is a legally binding contract between the user and the software publisher. And I think this is the case for the US, if I'm not mistaken. So companies actually, I don't know, tell a story, let's say. It's a rather slimy way of saying this, but they actually tell a story about what the software will do and how it will interact with the user, because once the user accepts the end-user license agreement, it actually accepts all the implications of it. So, do users really read this document knowing its importance? So, actually, I'm going to ask you, and how many of you do actually read the end-user license agreement? Please. Okay, not that many. Okay, actually, that was expected because statistics say that more than 50% of the users take less than 8 seconds to read the end-user license agreement, and that is clearly not enough. Okay, so this is mostly due to the fact that the terminology, the legal terminology, is hard to understand, and the language obfuscation that is sometimes voluntary might make reading this document a daunting task for the average user. And now I'm going to give you an example of such an end-user license agreement. So this is actually taken from the PayPal service. This is only the beginning now. And we're going to continue reading it. So this is still the beginning. And now we find something important. And more important things here. And more important things. Even more important things. And some important things with bullets. And some more important things. But because I like you guys, I'm going to stop here and show you a funny fact. So actually, all the text that I presented you here only has 1,257 words. And the PayPal end-user license agreement has in excess of 25,000 words. So imagine yourself reading this document. You, I don't know, wake up in the morning, get a nice cup of coffee, and enjoy reading this monumental document. And I was talking about language obfuscation in end-user license agreement. So here we have a piece of text taken from such a document. I've actually replaced the name of the software with the word software. This is a adware. So we collect non-personal and personal information in order to provide and operate software and to make software and related services customized as possible to your interests and preferences. We also use the information for statistical and analytics, research, and technical support. This enables us to further develop, customize, and improve software based on users' common preferences and uses, and to enable us to provide our users with a better user experience with more relevant products, offers, deals, and other marketing materials. So this actually looks nice, and you might actually think that this software tries to help you and improve your experience, but you might actually read this in a different way, and I've written there a shorter version. We collect non-personal and personal information in order to provide targeted advertisements. And now, knowing all this information about how documents are obfuscated and the legal terminology, this actually helps us in creating algorithms that can classify end-user license agreements. So this is a great task for natural language processing, supervised learning, and of course my favorite, Python. In order to achieve these results, we processed about 1 million Windows binary files in order to extract the end-user license agreements. And here we have the processing flow schematics. So we start with a file collection. The clean files were taken from known vendors, and the adware files were taken from our collection. We have a different process for working with nullsoft installers. I'm going to give more details immediately. And we have a generic unpack module that helps us better extract links and get them from online resources. And then all that information goes to the data processing. So the details I promised about the nullsoft installers. Well, they are processed differently because they actually offer a way of extracting the end-user license agreement and linking it directly to the installer. So we know for sure that end-user license agreement is from the installer and not a component from inside it or something installed by that particular binary. Next, we unpack all the files using in-house engines and publicly available software that can handle different packers. This actually helps us find all those patterns that we need in order to extract links and things like that, that ultimately gets us to a end-user license agreement or a privacy policy or things like that. And all that information goes to processing. Well, the first thing we do is split the text into sentences. Then we tokenize them and obtain the part of speech tags. After that, we strip the stop words because they actually they don't help in our algorithm. They're just noise. And we do some word sense disambiguation. Okay, that's a hard word. And feature extraction. And all these features are actually fed to the detection and classification algorithm. So now I'm going to give you an example of how this actually works. We have the original text. It's taken from an adware, end-user license agreement. The software is supported by various types of advertising displayed in your browser. These advertisements may be targeted to queries you make through your browser. So we first split this text into sentences. We obviously have only two. And for the remainder of this talk, I'm going to only take the first one. Okay. So next we tokenize the sentences, and we obtain a list of words. And you have it here with every word with an ID. And we obtain the part of speech tags. That is present on the third column on each of the two tables, and on the right we have a table with a description for every part of speech. So, for example, for the word software, we know that it's a proper noun, singular, and for example, various, it's an adjective. This actually will help us in later steps. We then strip the stop words, as they actually produce noise when fed into a algorithm like ours. Okay, now the word sense disambiguation. Okay, that's a really hard one. We actually tried a few algorithms for extracting a root form of the word. So we have Porter, Lancaster, and Snowball. These are all classics. Everyone working with natural language processing might have encountered them. So, yeah. And we also worked with WordNet. That's a little bit different from the others. And actually, in our case, it produced the best results. And using that algorithm, we can now change our text and produce a root form. So, for example, I have changed the color for the words that have been modified. The and software have remained at the same form. Yeah, I'm going to change that. Supported, changed to support. Yeah, various, changed to assorted. That's actually synonym. And type and advertisement changed to ad. And this actually helps us because a lot of similar words can translate to a unique word. And in the case of patterns, this is very helpful. So, after working with all these algorithms and processing the text, we actually did one thing that is rather, I don't know, custom when working with such algorithms. We extracted the top 10,000 words by frequency from the entire document lot, and I'm talking about the 1 million files. And we also did some combinations of 2 or 3 words from the sentences, and this is why actually we split the text into sentences, and we didn't work on the entire text. Because when we have a sentence and we can do so, this combination of words, we can actually extract sense from a sentence. So after doing this, we extracted the top 10,000 from the frequency of combinations. And we actually got a 20,000 list, 20,000 features, and that actually is not a feasible number to work with, and not when you work with large amounts of data, because the project itself was built to automate signing and for large amounts of data. And of course, when working with linear classifiers and things like that, having a lot of feature is not helpful. So we tested methods of filtering those features, and we have 4 feature selectors. And after we run all the information with them, the result is fed to the linear classifier that we called one-side perceptron. Okay, and here are the results. This is a rather interesting slide. It has mathematical stuff in it and a table. Yes, the table. I'm going to explain a little bit about what it represents. first of all, we have the column for the feature selector. It's actually the 4 feature selectors I talked about. Then we have the false positives from our tests for each of one, and the detection rate and accuracy. So for the first 2, those are with the mathematical functions. I'm not going to give more information because of time restrictions. But actually, they are pretty known when working with perceptrons and things like that. So actually, the procdiff and ABS procdiff are the ones that matter for us because they produce the best results. And procdiff is the difference between the percentage of clean and adware samples that share the same feature. And ABS procdiff is the absolute value of procdiff. So we can find that procdiff actually provides the best results. It's written in red there. We have a detection rate of 96.6% with an accuracy of 98.24. Okay, and for the conclusions, we were actually very pleased with the results because we managed to find ways that we can exploit the end-user license agreement into providing a generic detection for multiple adware families. And the thing is that most AV companies rely on 2 basic, let's call them basic, detection methods. That's the static detection that actually analyzes the file based on the binary content, the dynamic detection analyzing a file based on its behavior. And we think we found the third one, and that's EULA-based detection, that is detecting a file based on its creator's own description of its behavior. Because as I've told before, actually the end-user license agreement contains various information about what the software does or might do in some conditions. And of course, I like turtles. Now, for any questions?
I'm curious if you have any results on what the model looks like. Like, what are the 10 words that you either should or shouldn't put in your EULA?
Actually, the most powerful word combinations. So when we actually tried building a static engine for things like that with signatures, human-made signatures, and we found that combinations of words are the most powerful, and we actually managed to produce. It's not written in the slides, but you can find this in the paper. We actually managed to produce a 85% detection rate with 0 false positives using human signatures with word combinations. So I think yeah, we can talk afterwards, and yeah.
What about polymorphism? How would you choose, for example, from a huge text, as you put it, something that's actually quite relevant? I mean, in my head, I would choose something like advertising and so on.
Well, actually, this is an interesting question, and the thing is that when you talk about end-user license agreements, and I gave the example of PayPal. That particular end-user license agreement is huge. It's freaking huge. So actually, there are markers somewhere in the text, and those are the ones that make meaning from our point of view. So in an adware environment, the end-user license agreement might be 10 pages long or something like that, but it's enough that in one sentence it specifies that we are going to display adware. So some of these combinations, for example, we and display adware, have a very large score. So when you have only this one, it's enough to create a detection.
Were there any commonalities in the false positives?
Well, we actually had one funny false positive, and that's the end-user license agreement for Chrome browser. And Let me tell you why. Because if you read that end-user license agreement, it says that Chrome is actually a service that sends all the information and search queries to the servers in order to improve the advertisements that are displayed. So, yeah, we don't sign Google, but you catch the idea.
Thank you.
Are there any more questions lurking out there I can't see? Oh, sorry, over here.
Did you look on other languages besides English?
No. And that's a thing that we can improve in the future, but for now we're based on all the information that we already have for English, and providing a new thesaurus is actually difficult because grammar changes for every language and things like that, and when we want to have the root form for some words or things like that, it's very difficult because every language has its own rules. It's something that we can do in the future, but for now, most adware are in English, so it doesn't really, yeah.
Two questions. Are you using any sort of natural language processing library?
Yeah, actually, our tool is built in Python and C, and for the processing part, we use Python and LTLK. That's the library for natural
And is
language.
this largely intended to solve the problems with PUAs, not really malware, or?
Actually, it works really good. Yeah, this library is used for all the processing. I can show you. Okay. So everything here everything here is actually done with that library. The splitting the text into sentences, tokenizing, and obtaining the part of speech and things like that. Even the word sense integration, WordNet integration. Sorry, it's made using NTLK library.
Thanks.
Okay, do we have any more questions? In that case, I'd like you to show your appreciation for an interesting presentation from Stefan.